Yes, it's all-to-all personalized communication. Here, every processor has n elements, which are different, right? And it wants to share all these elements with all the other processors. So if I look at all the elements here, then n should be made known to processor n, and n minus 1 needs to be known at processor n minus 1. So it's personal communication. It has a message for every other processor, and all the other processors also have a message for the other processors, right? So that's why it's called all-to-all personal exchanges. It's also called total exchange, and that kind of happens in these kind of communication patterns. For instance, if I want to do a matrix transpose, which is a kind of classical operation in linear algebra, which is usually denoted by the letter T on the matrix. I mean, in matrix algebra, you get often these kind of expressions like A times V minus 1 times C transposed, right? So this is the inverse of the matrix B, this is the normal matrix, and you have to make the product of these kind of things. These are kind of the typical operations you see in these kind of numerical algorithms. And if I would have divided my matrix like this, that all the elements of rows, every individual row is connected to a processor element, then this transpose operation would occur an all-to-all exchange. Every element needs to be exchanged with another element somewhere in the matrix, right? This top element needs to be transposed, put here, and the other one here, this one here, and this one here, right? So that's the transpose operation. Now this is of course not a very nice operation, as you would guess, because in a ring what you typically could do is that you send all the items you have to the next processor, and this one takes the one away which it needs, and then you send the rest to the other one, and then it takes away the one you need, right? And so you go on. So you strip one element from the row each time, which leads to this kind of formula, because we need one round of P minus 1 processors. So it's the sum of one step towards P minus 1, and every time the message size is decreased by 1. So if you sum that up, it leads to this formula, and then if we reduce it algebraically, we end up with this formula. Now you immediately see that this behavior is not really nice, right? Because we have a P squared type of complexity here, being this P and this P multiplying against the transport time of the system. So for a ring, this is an expensive operation, this all-to-all operation, P squared type of complexity. Another question is this optimal? Couldn't we do better, right? So we have this. Is there not an algorithm we could think of which would do a better job than this P squared complexity? Because you might have overlooked something. Right? Now I'm not going to ask you whether we overlooked something, because that might be a brain drainer for you, and you're going to invent some fancy schemes which in the end might not lead to a better complexity. But we can also come up with another argument. And this argument goes like this. Each node in this system sends m times p minus 1 words at the first step, right? And then it strips one word at a time, which is equivalent to sending these m p minus 1 type of words to half of the nodes. Right? Now we have to travel on the average distance p divided by 2, and the total number of links is p, so the total number of words we transfer is m times p minus 1 times p divided by 2 divided by p. Now the communication time we derived was, the complexity was lower bounded by p minus 1 times p divided by 2. Alright? Now since we have p links, we see this expression also here. Right? And we see that it's approximately the same. So yes, indeed, we can't do better than that. So it has with a different argument, we come with the same complexity. Right. So this is optimal. What we can do. We can't do better in this ring example. Now the question is: does the mesh do better? Well. Again, we can treat rows and columns independently, being that the message size per is now n times the square root of p, and the number of processors is the square root of p. Now, with some calculations, it's a little bit better in the sense that we now do not have a squared proportionality, but the p here is replaced by a square root of p, so it's p times the square root of p, which is not too bad. I mean, p log p would be better, but p times the square root of p is kind of, what you could say, is reasonably nice, right? It's not too bad for this kind of operation. So the mesh is performing a little bit better, and that's, of course, not really a surprise, because you have, I mean, this all-to-all personalized communication is very communication intensive, and you have more communication links in the mesh compared to a linear array. Well, the hypercube is, we can do an algorithm like that. For instance, these two nodes have these sets of items, right? This one needs to be communicated to processor 1, this to processor 2, 3, 4, 5, 6, 7, and this has 1 which has to be sent to 0. This one it already has 1, it has to be sent to processor 2, etc., etc. And what we do is we exchange halves here. So after the first step, all nodes have to exchange in one dimension all halves. Right? So in the end, it picks out these items and sends it to processor 1, and it receives these items from processor 1. Not at the same time, because the links are bidirectional. Well, you can do the links are bidirectional, so you can do it simultaneously. It was one of the preliminaries in the right. So after this step, the situation is the wrong, I think. No, pressing the wrong button. So after this communication step, it has the 4 pairs which it didn't send plus the ones it's received from processor 1, and there it again makes a selection about half and sends it to the other processor. And this process continues until we're done. And then we have exchanged all the data items, and indeed we see here, and what you will kind of expect is that this complexity is P log P, right? Because we need log P steps to conclude. Here the message size is of course larger than one item, but it's equal for all steps. But it might be a little bit misleading here, because you might say the message size is somewhat larger, but it's true, but it's equal to the number of processors divided by 2. So we see that for the linear array it's p squared, for the mesh it's p times square root of p, and for here it's p log p. Now we can do the same argument. This is just an algorithm I showed you that works, right? And here again is the question, can't we do better? Because what you see here, for instance, is that in this second step you do not use these links, right? These links are not used at all, right? So you basically waste communication capabilities in the system. Well, we can do the same argument. Each node sends n times p minus 1 words to half the distance, log p. So the number of words we transfer is m times p minus 1 times log p times p divided by 2. Total number of links is p log p divided by 2. Right, so the communication time, right, if I divided this expression against this one, then the communication time is proportional to p minus 1. What did we derive in the previous algorithm? No, we derived that in our previous algorithm the complexity was p log p. And here we show with an argument that given the capacity we have, we should be able to achieve p, linear with p. Right? It's not an algorithm, it's just an argument. Right? So I have so much capacity, I have so many to send so many things and so on. So there might be space for an algorithm which is more effective than the previous one. So this is, the algorithm is not optimal. And indeed there is a different algorithm which is more optimal, and that's using the E-cube routing. And that takes p minus 1 steps, and this one shows only the 7th step, where each step, the communication is made up by the pattern. This is the node number I, and this is a step number. Then you can show that in each step you have non-conflicting roots at each step to make your communication hold. And that means that you can use all the communications channels in that case, because you only need p steps to exchange in a personal way all the messages you have. So for instance, the 7th step, you have this route made through cut through, so that's from 0 to 7, right? Then you have a route from can't tell the origin here because it's complicated. Oh, the arrows are okay. Anyway, these are the 7 route. These are the route patterns which are in the 7 steps. being done concurrently, and this is the other one, and this is the other one. So you have a number of routes which are totally using the cube to transfer the data between the nodes that have been selected in that step. And then the time is simply proportional to p. Right? So there is another algorithm for achieving personalized communication that is indeed, for the hypercube at least, proportional to p. So that shows that we can do a good job here as well. Is this all? No, there's one communication pattern left, and that is circular shift. Sometimes we need to shift a number of positions, the data items we have. And shifting occurs in many, for instance, imaging operations where you need to shift a mask or something like that over. Now in the ring, circular in a ring is simple, right? If you want to shift from node I to node J, it's simply this expression. So the communication time of the ring is then the minimum of Q and P minus Q, the other way around. So that is a simple thing. For mesh, it's somewhat more complicated, because here we have an example of a circular shift, where in the original numbered processors, each one has a data item which I number the same according to the original processor, and if I want to have a 4 shift, then I have to shift this one 1, 2, 3, 4 to this place. Now, of course, we can make a kind of circle, ring or snake through the thing and then shift it to these positions, but that is not necessarily the most efficient one. What you usually do is shift the item in first in the row towards the column position that it has to go up, right? And then shift a number of places in the column to get it in the right position, and not go through all the intermediate positions. So we first shift all items Q mod square root of P to this direction, but then we make a mistake, because actually this one should not appear here but a row higher. So we have to compensate then in the next step for the number of columns it had to pass, for the number, in this case, this one needs to be shifted one position up, because otherwise things are not in order. And then this one, which needs to be at this place, is in the right column, and then we can shift this column up. Right? So, and that's equal to Q divided by the square sigma function. Right. Sometimes we shift too much, according to the previous algorithm. And where is that? The 8?
8.
What 8?
The number 8. It's not in the right position. It shouldn't be at node or processor 6. If you do a 4 shift,
yeah,
then it would be at 0, 1.
No, this is before the column shift, right? For the column compensation. You're right, it's not in a good position, should be there. But the column compensation is the next step. Now simple, if we had a 100 shift, then we would shift until we're done, right? And that we don't do, right? No, that's not the right way of saying it. If this is long, I might shift too many places, while if I would go the other way around, then I would only have to shift one place. That is the Rush argument, right? So the middle, you can observe that one mesh dimension, we never have to shift more than half of the row, right? So the number of shifts is upper bounded by the square root of p divided by 2. So in a mesh, there the circular shift is upper bounded by the square root of p. By this simple argument. Sometimes we can even improve on one of the basic algorithms by making use of a clever trick. And I'll show you one. We had seen the one-to-all broadcast, and what we do here is doing something counterintuitively. We split, say we have a very large message M, very large. What we do is we split it in M divided by P parts. Then we do an all-to-all personalized communication. This one doesn't get they don't get equal copies, but they each get a part of the big M message, right? So we have a big message M. And each one gets a part of size M divided by P. This gives a complexity of what we have seen proportional to P, but the message size is smaller, M divided by P. Right? In step 2, we do an all-to-all broadcast, which seems not to be nice, but we have these messages here, but now they are of size n divided by p, and we broadcast them all to the all broadcast to all the other process elements, and then everybody gets the original message big N in its place, right? Now also here we can, just by filling in the original expression the communication time, which is equal to this expression. Then we add them up, right? And you've already seen that these things kind of fall away against each other, these terms. So we get an optimized one-to-all, which is not depending on P. This is extremely nice, right? So we have a one-to-all broadcast now by this mechanism, which is even constant complexity, not even depending on P. This is really nice, right? There's even a log P. This term, of course, for the startup becomes somewhat more complex because we use a splitted algorithm to do that. So that becomes more, the overhead becomes larger, and that is no surprise. So you can only do that if the message is really, really large, the data item, so that you can split it in n divided by p parts. Because if p is 1 million, right, you really need a large data item to do this kind of tricks, because otherwise it doesn't work, because then the overhead becomes really prohibitive, right? So let's go back to our assumptions. Thus far, the assumption has been only one message can be in transit at a time. Now you could say, and you said that before, the nodes have more than one link. And the question is, does it improve performance if we allow simultaneously send on all links? Well, there are several things to say. For Hypercube, it holds that one-to-all, all-to-all, and personalized communication are smaller by a factor of log p, right? So you can just divide all the expressions by log p. However, for a ring and a mesh, the number of links are constant per node, and there is no asymptotic improvement here. So only for Hypercube you have this asymptotic improvement, not for the others. But there's more to say. The messages must be large enough to be split through the multiple links. That's the first thing. This is extremely difficult to program, sending multiple sendings at a time. And if the computation to communication ratio is large, more advanced communication hardly does improve the overall performance. That's an other counter argument. And last but not least, the memory bandwidth must sustain the sum of the link speeds out to the outside world. Now, if we go outside the chip, that might be feasible. Inside is a different story. If I still want a single die, then the memory bandwidth might be high enough to sustain that. But go offside is a different story. It changes a little bit the arguments, but not too much. The bandwidth requirements of these operations, and I've summed them up on a hypercube, are order 1 for one-to-all, all-to-all, all-reduce, scatter, and they're order P for all-to-all personalized and circular shift. So these are the more important, more difficult operations to get efficient on any system. And they're also used in the sense that you might think I'm talking very abstractly, that they never use, but in every communication library there is an equivalent for these collective communication operations. So instead that you by hand encode these operations by using single message transfers in a loop, you can use one-to-all, all-to-all by having the equivalent library call in all these, for instance, MPI, use these functions, and hopefully the implementers of the library did a good job in implementing this efficiently. Right? So you have to be sure about that, because then it's not anymore in your hand. Because if they don't do that, you might end up with the wrong complexity. Right? Now, how do you know that that they do a good implementation?
Maybe it's a big company, so you should trust them.
Sorry.
It's a big company, so you could trust them.
Well,
And
usually.
they can test it on many
Yeah.
I think it should be tested in many clusters before they give a letter. So,
If the company does do it themselves, right?
more people, better result.
Not necessarily more people.
They are simple.
No, 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 no. That's too simple. If you, I mean, in software that generally doesn't help. Yeah.
You could do an empirical benchmark.
You can do a benchmark, right? Just run a simple program and see whether the complexity characteristics are reflected by your measurements, right? See whether it works or not. Even for some of these libraries, it's known that there are different implementations for different sizes of messages. Because if messages are small or large, then it can make a difference how you implement it. Or if the number of processors are large or small, it can also make a difference because the overhead then might in the end be prohibitive if the number of processors is too small or too large. I think that's it on this part of slides. So what I'm going to do next, we have a few minutes, so I'm not sure how far I can get, is to introduce you to the topic of performance modeling of parallel programs. As I said before, there are a number of sources of overhead if I go in parallel. That is, I have to communicate and synchronize with my neighbors. It might be that some of the processors are idle. It might be that I have to do some of the computations double, because do it on one processor and then sending the results might be prohibitively expensive. So these are kind of sources of things. But if we're going to talk about performance, we need performance metrics. Of course, the starting point is the serial execution time. That is the time the program takes if I run it on one machine where we start it. And the counterpart is the parallel execution time. If I multiply the parallel execution time with the number of processors and I subtract the serial execution time, I end up with the overhead necessary. If it's perfect, I've done a perfect job, this overhead is of course zero, because then, yes?
Can the overhead be negative?
No?
I know it could take like less time to parallelize. Okay.
If the, I'll come to that. In theory, yes. I'll probably come up with an example. The speed up is defined as the serial best against the parallel execution time. That's the speed up. And I deliberately put here serial best because in my effort to parallelize things, I probably might have to change things. I might have to change the algorithm a little bit, and then we're not talking about equivalent programs anymore. And we have to be careful about that, because of course I can also run a parallel program with P is 1, and that's not the same as serial best. To give you an example, suppose I have a program with an execution time of 100 units, while the runtime of my parallelized program, if I have one processor, is 200, and P, if I use 4 processors, it's 75. Then if I would take this one, I I would conclude that my speed up is 2.6, while if I do this one, it's only 1.3. And this is a mistake people frequently make, also in the literature, right? So they make a graph, and they parameterize their parallel program, and they say, well, I compared it against PS1, and that's not fair, because you've changed things, right? So you have to, the only solid baseline is the serial execution. Okay. Let's look at if we can start with a very simple performance model of adding n numbers on n processors. I have n is 8 processors here, and I'm going to, each processor contains a number, and we're going to see what the time complexity of this operation is. Well, the most logical algorithm is that we do, in the first step, things pairwise, right? So this processor sends its data to this processor, and then it adds up, and the other one also doing that. And the logical next step is that half of the processors have the result and do the same trick again. Right? And then finally, we do in the last step that the final result is added. Now, what can we see about the runtime of this program? Then we have to make an assumption that each time step takes a constant amount of time, and that each step consists of one addition and one communication step. In that case, we can conclude that the parallel execution time, which is run like that, is log n, right? Because we have a binary tree reducing to a single number. And by definition, my speed up is n over log n, right? I think I'll stop here because I'm going to take you to somewhat more complex argument, and I need some time for that, and otherwise I have to stop in the middle of the argument, so that's not what I should do exactly. So we will continue with this example. I'll repeat it next time on the